Hi everybody, welcome back. We are ready for the second half, if you will, of lesson 3.5. Now we covered lesson 3.5 a couple of units ago and we focused only on solving things. And the things that we were solving were exponential and logarithmic equations. So we are back to solving exponential and logarithmic equations, only this time we're doing it in the context of some word problems, okay? And understanding what do these answers really mean and do they really make sense. Couple of things to remember from Unit 1 and Unit 2. Exponents and logarithms are inverses of each other. That means they undo each other. So if I have something with an x in the exponent, to undo it, I'm going to use a logarithm and vice versa. So you might want to keep these couple of properties in mind as we go through this. Again, this was one of those lessons where you definitely want to know what your calculator is doing. And so if you have any questions, make sure you come on in and talk to us. All right, let's hop into it here. First example, we've got the radioactive isotope germanium-71. It's decaying at a rate of 6% per day. And the scientists originally had a 15-gram sample. So what we want to know is how long will it take for half of that sample to remain? Okay, the first thing we need to do is create a model. So as soon as we see that we are decaying or growing at a percentage rate, our brain should think exponential. So we're going to go with y equals ab to the x power. And keeping in mind from our exponential unit earlier, we know that the A is the original amount, so the scientist had 15 grams to begin with. And if we are decaying at a rate of 6%, that means we lose 6%. If we're going to lose 6%, the question is, how much are we going to keep? Well, that means we're going to keep 94%. Kept, if you will. Okay, so if we're going to keep 94%, that is our B value as a percentage rate, and we're going to need our B value to be a decimal, so we're going to change that to a 0.94x. Now, keep in mind what is x and what is y. X is going to be our time, 6% per day. So again, keep in the good habit of labeling whatever variables you choose and describing them. Number of days for x, okay? Y in this model is going to be the amount of the germanium-71, if you don't mind, I'm going to abbreviate, that is left over after that many days. All right, so far so good. So now we have created a model, and we're going to use our model to determine how much germanium, how long it will take for the sample to be cut in half. So if the sample is going to be cut in half, half of what? Well, we're talking about half of the original amount. Half of the original amount is going to be 7.5, because that's half of 15. So let's come over here. We're going to have 7.5. And it's going to equal 15 times 0.94 to the x power. And we are now ready to solve because we have one variable left. Again, our variable is the x. It is in the exponent. In order to solve it, we're going to need to be able to use a logarithm. Before we get that far, we need to have 3 pieces. I have too many pieces. I have a 7.5, I have a 15, I have a base, and I have an exponent. So I'm going to go ahead and divide both sides here by 15. No surprise here, I'm going to get a half, hence the name half-life. Okay, now we got 0.94 raised to the x power. Now we've done these problems with a graph, and we graph both sides. The y1 would be 0.5 and the y2 would be 0.94 to the x, and see where those two things cross. We're just going to go ahead and do it algebraically now. So how do I get the x out of the exponent? I'm going to apply a logarithm of both sides. Now this is where you want to know, what is your calculator doing? I know that my calculator does have the log base button, so I'm going to use the base 0.94 that I already have, and I'm going to apply that to both sides. Excuse me, that's going to be 0.5 right there. All right, so I'm going to go log 0.94 on the left side, and it's going to equal log of 0.94 on the right side. And if we take a look at the left side, this is just something I can type into my calculator at this point. On the right side, log base 0.94 of 0.94 raised to the x is simply x. Okay, so typing all that into my graphing calculator, I will end up with 11.202. And remember, those are days, because we assigned x to be days. I promise that says days in the beginning. All right, again, any questions on how your calculator uses its logarithm buttons, please come on in and talk to me. If you have a TI-83, you're going to have to use a change of base formula right there, or use a log base 10 in the first place, or a natural log in the first place. All right, very simple exponential problem. Moving right along. Let's talk logistic. Logistics we've gotten into a little bit more in this unit, and here's a situation where we would use some logistic growth. Okay, environmentalists will take an endangered species and they will capture it, and then they're going to move it somewhere else and release it so that it can produce more offspring. So it's still in the wild, but they moved it to a new place in the wild to sort of regenerate its population. Okay, if you've ever seen the Disney, I think it's a Disney movie. Anyway, if you've ever seen the movie Rio, that's kind of what was going on. So here's our problem scenario. We've got 8 American bald eagles, and they're captured and they transport them to Montana to see if they can get them to grow. They're going to set them free. Based on experience, the environmentalists have created this population model, and it's right here given to us. Okay, so this is going to be the population of the eagles after T number of years. Okay, all right, so the question is, how long, that's a time, how long will it take for the population to reach 250 bald eagles? Okay, be good readers. You might have to read these problems more than once, and that's okay. How long to reach 250 bald eagles? 250 is a population, so I'm going to plug it into my population number. And I'm still going to have my model with my 500 divided by 1.61.5 e raised to the negative 0.162 times t. Be careful with your t's. They're going to look like pluses. You might want to put a little cursive -y on them. I'm sure that's not that. It's probably Danielian or some fancy handwriting. Anyway, okay, so what do we need to do? We need to get an x out of an exponent, or a t in this case out of the exponent. We can't do that for a lot of reasons. We've got a whole bunch of extra numbers, our t is in the denominator, and there's a whole bunch of things with the base. So what you might want to first do is identify what is the base that we are trying to isolate. This e to the 0.162 is the piece that we're trying to get by itself. So first things first, I don't really like having fractions in problems. So if we multiply both sides by this 1 plus 61.5 e to the negative 0.162 on both sides, then we're going to end up having 250 times that denominator of 1 plus 61.5 e to the negative 0.162t equaling 500. Okay, now we could distribute our 250. We could. However, that's not going to help get numbers away from our exponent t. So instead, what I like to do is go ahead and divide by 250 at this point. So now I have 1 plus 61.5 e to the negative 0.162t, and 500 divided by 250 is just 2. Now, when you go to do that division, if you get not a very nice number, just leave it as a fraction. Okay, again, we are still trying to isolate the base, e to the 0.162. That's what we're trying to get by itself. So what else do we see? Well, I see a 1 with it. I see a 61.5 with it. So let's do a little bit more arithmetic. So we're going to go ahead and subtract our 1 on both sides. And now I have 61.5 e to the 0.162t. And 2 minus 1 is 1. And now I can divide by 61.5. Now again, that is not going to be a nice number. So I'm going to leave it as 1 divided by 61.5. Okay, good. Now we are back to where we were in lesson 3.5, where we're dealing with only an exponential. We've got one base, one exponent, excuse me, with an extra number of 1 over 61.5. Okay, so now how do we undo an exponent? Well, we apply a logarithm. We apply a logarithm with the same base as whatever the exponent had in the first place. So I'm going to apply a natural log to both sides of this equation. It's going to get a little messy there, sorry. And so now I have the natural log of e to the 0.162t, only the natural log, which is the base e, of an e to an exponent is simply my exponent. So I'm left with 0.162t equaling the natural log of 1 over 61.5. Okay? So far so good? What was I trying to get by itself? I was trying to get t by itself. How on earth am I going to get t by itself? Well, I'm going to come on up over here. And I'm going to get t by itself by dividing by negative 0.162. Now that's going to make kind of a mess when I go to type it in my calculator. So instead of dividing, I can always, instead of dividing by a fraction rather, I can always multiply by its reciprocal. So the reciprocal of negative 0.162 is 1 over negative 0.162. And then we're going to have the natural log of our 1 over 61.5. The board doesn't really like me on this left side over here. Go ahead and make that a little prettier if I can. 61.5. Okay, that's as good as it gets. I did isolate the t. Now all I have to do is type all that into my graphing calculator, being careful of my order of operations and my parentheses, and we are going to get that t equals 25.426. And again, since this is population measured in years, it would take 25.426 years for our bald eagle population, which started at 8 bald eagles, to get to 250 bald eagles. Okay? Assuming we didn't have anything catastrophic happen in the meantime. All right, so we've covered exponential, we've covered logistic. What's left? This would be where Mr. Leckie would say logarithmic. But he's not here, so I'll do it myself. Logarithmic is left. Okay, so one last equation for you. We have this law of absorption. This is the Beer-Lambert law of absorption. And it's applying to Lake Erie at this time. And it's talking about the intensity of light. So what happens in a lake? Well, the water's not very clear in a lake. The further down you go, the more difficult it is to see, and the less intense the light is. Okay? So this light is being measured in what's called lumens, and it's at a depth of x feet. Okay? So they've given us an equation. By the way, if you're curious, notice how the variables are on both sides, but neither variable has been isolated. We're going to call this an implicit rule as opposed to an explicit rule. An explicit rule would have either I equals or x equals. So just a fun fact for you. I'm sure I got to go repeat that to everybody. Okay, what do we want to do? Well, we want to find the intensity of light, which is the I, at a depth of 300 feet. Okay, if the depth is 300 feet and the depth is being represented by x, all we have to do is do a little plugging in here. So we're going to have the log of I over 12, and it's going to equal negative. Now watch out with these decimals. These are not pretty numbers. Double check them, okay? We're going to have negative 0.00235 times 30, okay? Simply plugging that in. Our goal now is to solve for that I. Now, I did go ahead and multiply these two numbers on my calculator, and I found that they are a terminating decimal. In other words, they stopped repeating. They didn't repeat and go forever. So I can just write down all the decimals as long as I'm not rounding and creating a rounding error. So I have 0.0705 when I multiply those two numbers together. Now I have the logarithm of I over 12. Again, what am I trying to isolate? I'm eventually trying to get I equals. Okay? I can't get I equals right now because I is built inside of a logarithm. How do I undo a logarithm? Say it together. Use an exponent. Okay? What is the base of this logarithm? Well, this logarithm doesn't have a base, so it's a base 10. So what that means is I can take both sides and raise it to a power with a base 10. So I'm applying it into an exponent rule. Now I've got 10 raised to the log base 10, which all basically undoes each other, and I'll be left with I over 12. And on the right hand side of my equation, I'm going to have 10 raised to the 0.0705. Just a guess, that's not a pretty number. It's going to be a small number because 10 raised to a negative will be a number 1 over 10 to the 0.0705. Okay, what was I trying to do? I was trying to get I by itself. Now all I have to do is simply multiply both sides by 12, and I will get I equals. Type it into your calculator. Make sure that you are multiplying, or rather raising to the power only the 10 part. You cannot make it 120. That is breaking the rules of algebra, so don't do that. And we'll get approximately, these are all rounded answers, 10.202. Now I is intensity. What were we measuring intensity in? We were measuring it in lumens, so these would be lumens. If they give me a unit on my question, I'm going to make sure that I put units on my answer. Okay, the other thing that we will cover when you get into class is a little bit of logarithmic and exponential and logistic regressions. They're going to work just like your other regressions did, so make sure you have your calculator in class. I'll see you soon.